Chat today, and we're very excited to be speaking with the team from the University of California at Irvine called Cognitive Power Management. Joining me, Tiffany Fox, are Fadi Kurdahi, Professor Kurdahi, and Amr Hussain. And remotely joining us is Muhammad Abdul Ghaffar, who's also a member of the team. We will be joined as well by members of the Cal IT2 at UC San Diego staff, including our director, Ramesh Rao, who's one of the competition judges. And we also have Joseph Gradone of InterDigital. He's a member of the technical staff there, joining us remotely. He'll be participating in the chat. The way this will happen is we will have a 5-minute presentation by the members of Cognitive Power Management. We'll follow that up with 10 minutes of questions from the staff and faculty at Cal IT2. And then we'll open that up to 10 to 15 minutes of questions from anyone who's participating. If you have a question during the chat portion, please type it into the chat box, and we will take those questions from there. We will also provide the question to our Cognitive Power Management team, so you can read it in the chat box if the question somehow doesn't make sense the first time around. So without further ado, let's get started and hear from Cognitive Power Management.
Good morning, everyone, and thank you for inviting us for this presentation. We're excited to be among the finalists and look forward to telling you about what we're doing. So my name is Fadi Kurdahi, and let me start my presentation by going through some motherhood and apple pie type of thing, where we know that Moore's law for the past 50 years has been at the heart of the revolution that enabled us to design and build ecosystems that are transmitting data at an ever-increasing, exponentially increasing rate and volume. And that has resulted in providing services to consumers that are increasing in longevity and the kind of service, the quality of services. That positive feedback loop whereby technology provides these capabilities to consumer products, and consumers in their turn will exert pressure on the technology to ever innovate, has resulted in mobile being perhaps the most ubiquitous service on the planet, edging away people a number of people that have electricity, safe drinking water, and other services. Now, with that is not just all good news. There's something called the power challenge that has emerged as of late regarding the fact that we are putting more transistors on a chip, and it turns out that a large portion of those transistors are actually memories that reside on the chip. Now, together with the logic, those memories consume an ever-increasing amount of power. We're switching transistors faster, there is more leakage, leaking current, and so you can see here that the power consumption is increasing every year of a typical handset and is expected to soon exceed the power density limit of the handset that is determined by the size and the storage capacity of the battery. Now, that problem also resulted in an energy gap whereby the expectation that I can keep my phone not charged for 2 days and still sustain the kind of new services introduced by the providers, the content providers, is becoming less and less possible, creating an energy gap. So how do we combat that? Well, we have to realize that power is the key issue here, and we have to look at memories. So one way to reduce power is to lower the supply voltage. We know that that reduces both types of power, leakage and dynamic, by quadratic and exponential respectively. But there's a problem of variability, whereby in the past we were able to design chips that satisfy specific targets of power and performance. Today there's a large variability. Now, if we take a memory, for example, what does that mean? We have millions of cells, and they're all expected to operate at, let's say, 60 picoseconds access time. In reality, they don't. So we can see here that only a small portion of them will fail with that requirement. But as I start reducing the supply voltage, the problem becomes worse, and you have more and more cells failing to the point where the memories become unusable. So on the other side, I have to keep the supply voltage high, and we have this tug-of-war situation. Now, how do we get out of that? Well, we have to realize that we have to change the way we design things on a chip. For example, memories today are designed in a binary mode. They either operate at the nominal supply voltage, as you see it in the maroon curve, or if they don't, then they consider to fail. We really have to think more like a communication systems engineers, thinking of memories as noisy channels. And so now they're starting to look, you can see this duality between what communication system designers know as waterfall curves, and in the memory domain that is called the probability of error curve. So we're now thinking about memories as another channel that contributes supply voltage dependent noise. Now we can exploit this situation in a receiver. A receiver is typically designed to operate at the worst case signal to noise ratio, but it's seldom, is not often in that case. So a power management scheme that is cognitive might actually track the signal channel SNR and set a target SNR so that when I'm above that, I have enough of the slack and I can afford to roll supply voltage on the memories in the receiver, introducing additional noise, but that can also be fixed by the forward error correction decoder. Now that would be easy if the statistics of those noise in the memory is similar to the channel statistics, but they're not. So we have to change a forward error correction that can correct for both hardware and channel. So the first thing we did is to model that mathematically, and you can see here the model that we have come up with. And then we modified the forward error correction decoder to essentially account for that different statistics. You can see the performance of that decoder compared to a conventional Viterbi in this case, whereby the conventional Viterbi has a noise floor 10 to the -3, whereas in our case, the modified Viterbi has a pretty good performance, only slightly worse than an error-free environment for a given target memory error rate. The overhead for those decoders modifying them is very small, less than 1%. I'm going to show you a demo now, and we're going to quickly show you a video. So this is a system that we have. Actually, you can see it in the back. It's two work boards there with diversity antennas. We actually are transmitting an image, and then the image is transmitted over the air. Then we have a simulator on the laptop that's running MATLAB code that simulates the fault-tolerant buffering memories, and we have a choice of conventional or modified decoder. I'm going to just fast forward through that. As you can see now, there's a lot of noise. You can see the residual error here. And if I can switch in midstream between conventional here and modified decoder, you'll see now all of a sudden the noise drops significantly. And I have very little, if any, noise. And you can see the picture here. It's noisy on the top where I use the conventional decoder, and it's almost noise-free on the bottom. Now, we have also came up with a MATLAB environment that allows us to simulate that whole system, whereby we track the slack in signal to noise ratio, and we switch the voltage up and down, realizing power savings here, and we can set the target bit error rate. So the user can explore different power management policies that will enable them to take maximum advantage of the design of their receiver. And this is in a short our system. I'd like to thank you for your attention, and we'll be happy to answer any questions.
Thank you very much for that presentation. And we'll move on to the questions from the staff and faculty here at Cal IT2. My first question for you is, do you believe your team would benefit from additional expertise at this point? And that includes marketing, analysis, prototyping. And if so, what expertise would you be most hopeful to collaborate with?
Thank you very much for the question. Both Professor El Tawil and myself have had stints in the past with startup companies whereby technology was transferred from the labs into the market. And we are very much aware of the importance of having the right story being told and being at the right time at the right place in the market. So yes, I mean, I think this technology has a significant advantage, has a significant potential, and help on different fronts. marketing and is important, but also a lot of engineering work that has to take this from part simulation, part silicon, part MATLAB code, part puzzle, and put it together into a product or set of products that can benefit the target audience. In this case, would be the handset manufacturers and the content providers.
Okay, I was just about to ask you who your customers were, so you already answered that. What would you say is your product's greatest weakness?
That's a good question. I think there's a lot of engineering work that has to go into this to validate further in silicon. There's also other issues that come into the picture. That is today, for example, manufacturers are introducing new types of transistors, FinFETs. There's also on the horizon nanotechnology. We still haven't explored all of that. There seems to be promise in what we do from a conceptual point of view. However, the devil is in the details, and a lot of these issues have to be resolved before this becomes actually a viable product. It has a short, let's say, it has applicability for current technologies, but looking forward 5 to 10 years into the future, there needs to be some additional validation.
Can you elaborate a little bit on the applications for nanotechnology?
Well, for example, today memories are being replaced, or people are considering that in the future you're going to have different types of memories. So, for example, memristors. And so these will take a lot smaller area, but they have some issues associated with them. And we don't know, we don't have enough models for how they behave. People are still scratching the surface on this, but it's one of the promising technologies. There are other types of memory technologies that are also being proposed. And as since our domain is right now memories, it's really that becomes an issue if we're looking at the medium to long range. Like I said, for the short range, this has immediate application. Now let me add to that one other thing, which is we're only looking at memories in the current project, but we are switching to also logic, because that's another part of what resides on a chip. The transistors are divided between memory and logic. So that becomes a lot more difficult to model noise through logic. But it's something we believe the problem is solvable, but it's just going to take us time to go through that.
Okay, you alluded to the landscape in 5 to 10 years. Assuming that your technology is implemented in the marketplace, how do you foresee it changing the wireless industry as a whole?
Well, as you can see from the beginning of the slides, there seems to be an ever-increasing energy gap. Consumers are expecting to be able to play their videos for a longer time, to have, and also even more services coming up, online gaming. All of these things are hogs for power and memory. So it is a ripe fruit, whereas we deal with a situation where you have to consume a lot of power and you have a lot of memory that is at the heart of the power consumers. So we essentially see that as a big plus for our technology.
Okay. What have been some of your failures in developing the technology, and what have you learned from overcoming those failures?
We learned that if you don't succeed, try again, I guess. So there are things that we didn't consider in the past, and as you start going through the details, you see that, for example, temperature tends to affect the error rate, so you have to consider it. How do you, so one of the things that we have to do, for example, when we're also applying the same thing to video, and in video you have to kind of keep track of the defects in memory, and that's very hard to track, so you have to go back to what people that do chip testing do, because that's what they do for memories. They have some built-in self-test structures, and we have to learn how this works and then apply it for our technique. So it becomes almost like an operating system where you have a disk and you have a defect map on the disk, and somehow the operating system works around that. We have to get to an environment where we should be able to design systems that have reliable operation using unreliable components. It's something that transpires not just power consumption, but as I alluded to in a few minutes ago, memristors and other new nanotechnology devices have some inherent reliability problems with them. We have to learn how to build systems even though you have unreliable components that are part of that system. And somehow we have to change our concept of what is considered to be a functioning system and what is not functioning.
Okay. We'll have one more question from Cal IT2, and then we'll move on to the questions from InterDigital. And I wonder if I can hear from Amr on this one. Amr, could you describe your role in developing the technology, and then also answer what you feel are the top 3 qualities a successful entrepreneur should have?
Okay, so my role basically is to develop a reliable system. So what, as Professor Kudahi said, we need to build reliable communication using unreliable hardware. So my role is how to take this unreliable hardware and play with it to be on the same lines, just as using reliable hardware, have the same quality of service, so the user can have the same quality. I have considerable energy consumption. So basically, this was my my major role.
And then the second part of my question is, to be a successful entrepreneur, what 3 qualities should you have?
Okay, so basically, to be a successful entrepreneur, basically I have to get in depth with the market requirements. So just you know, to be able to know how does technology develop, and what are the market needs, and how can we link our stuff to the market. So so basically link the technology and what we do to the market requirements and market needs.
Okay. All right, thank you. We'll take a question now from Ramesh Rao, who's the director of Cal IT2 at UC San Diego, and he's also one of the competition judges. His question is, can your methods be used to identify parts of the memory that can operate reliably at low voltages? In other words, how random are the errors in space? And that question will appear in the chat box. You can read it for yourself.
Great. That's a very good question. Thank you, Ramesh, for the question. Yes. To answer the first part, yes, we can identify parts of the memory that can operate reliably at low voltages. In fact, so one of the things that we do, I alluded to video in the past. So what happens if we use those same memories or different kinds of memories? So today you have, for example, your companies like Qualcomm and others build application processor and modem processor or communication processor on the same chip. They have huge amounts of memory. In video, you need huge amounts of memory to store the decoded frames, so you can use them to decode future frames. Now, these are images, and you can see, for example, the image that I showed you, there is noise in the image, but there are ways to compensate for it. So filters, for example, can be used. The key, though, is to target only those faulty memory bits in the memory, and only fix those pixels that happen to be in those memory locations. So what we do is we use the existing infrastructure that designers put on chip, like built-in self-test, which scans the memory array at different voltages and keeps track of where you have failures. Again, kind of like a defect map that you have on a disk today. And then we have filtering that only targets those pixels, and you can fix the video. And the same thing can be done for wireless systems. So when I know where the errors are, I have a big advantage, and I can fix them. There's a caveat with that. As temperature rises or falls, there's additional failures that might come up, or failures that might disappear. So you have to run your built-in self-test on a kind of a periodic, but not too often, so that not to consume too much energy. The errors are, if they belong to random dopant fluctuation, which is the dominant phenomenon that manifests itself in, let's say, 45 nanometer and below technologies, they happen to be random in space. It has been proven in the literature. And so for the most part, those errors can be assumed uniformly random.
Okay, and we're losing you a bit on the webcam, so if you might center it a little better, that way we can see the both of you.
Okay.
We're going to take some questions from the member of the technical staff from InterDigital, Joseph Gradoni. I apologize if I'm saying it incorrectly. The first question has several parts, so we're going to go ahead and paste it into the chat box, and I'll read it aloud once. The question is, what are the assumptions of your simulation test case? And that includes the total gate count, memory bits with voltage reduction, total ASIC power, test case used for power savings results, and any 3GPP test cases. If you can address those sub-questions, that would be great.
Okay, so for our simulation test case, we assume that we have mainly random or independent errors in the memory. So each cell has independent error rate, independent error with the same probability of error rate, and the probability of error rate in the memory is highly dependent on the voltage level. For the total gate count and memory count, so actually this idea is applicable for higher memory size. So if I have a large portion of the chip, like for example the DVB, I can have around 6 megabytes of memory. So reducing the voltage has a considerable effect on the energy saving. So basically,
So also, I mean, to answer part B of the question, all the memory bits receive a voltage reduction. What happens is some memory bits will fail in the access time while others will not. So basically, there's a variability there, and so the error rates we have characterized the. It depends a lot on the sizing of the memory cells, whether you have minimum minimum area bit or increasing the size. That has a big effect in combating variability. So it really depends. But for example, in video, we can sustain error rates up to let's say 4%. So of all the bits, about 4% can still be failing, and we can still fix the videos. Power savings can be in the order of 40 to 50%. As you saw from the slides, reducing VDD from let's say 0.9 to 0.65 can actually give you a power savings of 50%. Now, we have also done similar work with processor caches, and there you can achieve even higher reduction. We were able to operate memories that sit in caches at below 0.5 volts, and that will give you power savings of the order of 80%, because in processors, leakage for memories and caches tend to be dominant, and that responds very nicely to voltage reduction, exponentially, that is. We have done 3GPP test cases. In fact, my colleague Ahmed has actually designed a 3GPP chip with diversity, and we have done test cases on that, looking at the memories there and gauging how much power savings can be done. In that case, this chip was designed before, even though it was not redesigned. Just by lowering supply voltage on some key memories on the chip, we were able to get about 20 to 25% savings in power. That's pretty huge for manufacturers. If that can be done in a design from scratch, you can achieve even higher power savings.
Wonderful. Okay, and we have another question from Mr. Berdoni. And I should note that he was proactive and sent these questions ahead of time after reading your submission proposal. So if any of these questions have already been addressed, it's not because he's asking questions you've already answered. The question is, your white paper said only FEC memories had voltage scaling. Processor memory cannot tolerate voltage reduction. If you care to comment on that. We'll paste that into the video chat box as well.
Very perceptive. So let me address that. First, from a conceptual point of view, yes. I mean, it goes without saying that the control flow in a system should still operate flawlessly. The data plane, if you like, can, in some cases, in many cases, I would argue, sustain some glitches. How many depends on the type of application. However, as I mentioned before, a big part of the processor memory happens to be cache. And a cache is what you can think of as a transient memory. In other words, I can actually, for example, take instruction caches. I could lower the supply voltage on the caches, and actually we've done that. We've had several papers on this domain. We can actually track the defects in those caches and If there are failures when you access them, you disable the cache line, or you have a small victim cache that can allow you to store the error-free versions of that while reducing the supply voltage on the whole cache. You can also play around at the circuit level with boosting the word line for those rows that have defective memory cells. We've tried many techniques, and as I mentioned, we were able to sustain supply voltages below 0.5 volts. Intel has done similar work after we did our work and have corroborated with chip designs that this is doable. In fact, there was a paper just this year in the ISSCC conference from Intel that have designed a chip that has techniques that are very similar to our circuit techniques for cache power reduction, and they validated some of the concepts that we have proposed. Yes, you are right. Forward error corrections are not currently 6 megabytes. What Amr was referring to was the DVP memories.
Yeah, and in general, we refer to the memory in the whole system. Like, for example, if I'm implementing a wireless communication standard, I have a lot of memory in the processing chain. Like, for example, if I am doing a 2D channel estimation, this requires a huge amount of memory. We assume when we say fake memories that we lump all the memory in the system into one big memory, and we study the statistics of this memory, and we modify the fake to handle the error in this memory. We don't mean the internal memory in the fake decoder. We mean the memory in the whole system.
Okay, thank you for clarifying that. And another question from Mr. Godoni. What is the assumed timing margin for the memory with reduced voltage? And a subset of that is, if the memory has a very tight timing budget, allowable voltage drop will be minimal, i.e. no power savings. And you can see that in the chat box.
Okay. Just look at this real quick here. Okay, let me answer the second part while Amr considers the first part. So, if the memory has a yes, that's true. However, it's the way people design memories these days is that they set the access time to a point that is defined by several variables. One of them is the mean access time. So you consider that the cells have variability. And so you have the mean access time plus some constant times the standard deviation plus some other constants. So they built in safety margins because they insist that memories have to operate flawlessly. In fact, they go further than that, they tend not to even touch the power supply for memories. But all we're saying is that it's true that if you have a very tight timing budget, it basically it means that insisting that all the memory cells have to operate flawlessly, 100%. If we can allow some of the cells, a small portion, to fail and compensate for that, as we did in this project, then that could give you some slack that otherwise you would not be present in a 100% error-free situation. Let me point out that the IPRS themselves have asserted in their latest prophecies they put online that 100% error-free chips are no longer sustainable economically. And so we are taking that to realization in our work.
Okay, and Amr, in the last minute, if you could address the second part of the question.
The first one, the exchange margin.
I guess I kind of answered that.
Yeah.
Okay, fine. Okay, well, we basically have covered the entire 30-minute Q&A session. So unless there's something you'd like to add about any of the questions, I think we can wrap it up. And we really
thank you for a very perceptive question. Thank you very much.
And thank you to all of those who participated in the chat. We really enjoyed hearing from you, and we hope to hear more from you as the competition continues. Best of luck, and we'll talk with you soon. Thank you.
Thank you so much. Thank you. Thank you for inviting.